So hello everyone. So in this video, this is the last amplifier we are going to discuss. In this video, let us discuss transresistance amplifier. So it is also called shunt feedback. Also it is called voltage shunt feedback. Okay, so it is also called voltage shunt. So by this time you should have understood. By this video you yourself should know. So why it is called shunt feedback or voltage shunt feedback? It is called shunt feedback because at both input and output side we have connecting a parallel connection. So and why it is called voltage shunt is, so output is voltage, and output is voltage, and at the input side we are connecting, making parallel connection. So in this transresistance amplifier, input is current, output is voltage. Transconductance is ulta, input is voltage, output was current. Here in transresistance amplifier, input is current Is, output is V0 voltage. Okay, so at both input and output we are making a feedback connection. Okay, so in this resistance, in transresistance, both input and output, input resistance decreases, input resistance decreases, that is I'll write RIF. Also output resistance also decreases, I'll write, and here also decreases. Okay, so this is the feedback block diagram of a shunt feedback, where both the input and output is parallelly connected. So input is Is, we have a source resistance Rs. For current we need to connect it parallel. So output is V0, so output load resistance we have connected RL. So we are sampling here voltage and giving to feedback network. So input to the feedback network is V0, output from the feedback network is IF current. Okay, so now beta is equal to in output IF divided by V0. Okay, fine. So this is the example for the feedback topology, that is shunt feedback using inverting op-amp. So this is the inverting op-amp configuration. Here we have connected a source. So for this connection we have connected a source, current source. So RS, since this is current source, we have connected RS in parallel, and the output is fed back to the input. Okay, so this is the shunt feedback using inverting op-amp. So for this amplifier, transresistance amplifier, will find what is the input resistance and output resistance. So in this case, input resistance and output resistance with feedback should reduce. Okay, so this is like I just wanted to show how AF is equal to A divided by 1 plus A beta for this circuit will come. So we know that this is not important, so only this part is important. So just to explain you, I have written this. So AF is equal to V0 divided by Vs. So what is V0? V0 is, but what is A? I'll write here. What is A? Gain. Output by input. What is output? In this case, transresistance amplifier, voltage is the output, current is II. Okay, so for V0 I can write A into II. A into I. What is Is? Is is II plus IF. Okay, that will not change at the input side. Okay, so here we are getting the feedback, output of the feedback network is IF. So this II, what we give here, will be Is minus IF. Therefore Is is equal to II plus IF. Okay, so that I have taken II plus IF. So AI IF. But what is IF? IF is beta V0. So that I explained later, before itself. AI is equal to IA plus beta. But what is V0? AII. Okay, so I've written AII. So III will cancel. So AF is equal to A divided by 1. This is standard for all the amplifiers. You can derive the same way for all the amplifiers. This is not necessary. You just wanted to know AF is equal to A divided by 1 plus A beta. Okay, so next we'll see what is the input resistance with feedback. So the input resistance with feedback is Vi divided by Is. Input resistance divided by Is. Okay, so I have told Is is equal to Ia plus If. Okay, what is If? Beta V0. So next what I had done is, so I have divide both numerator and denominator by Ia. So what I have done, Vi divided by Ia divided by Ia plus beta V0 divided by Ia. So what is Vi divided by Ia is, Vi divided by Ia I can write it as Ri. So Ia will cancel 1. What is V0 divided by Ia? So V0 divided by Ia is A. So I have taken this here. Rif is equal to Ri divided by 1 plus beta. So that what we are saying, the input resistance with feedback is decreasing 1 plus beta A times of Ri. So if this value increases, Rif will decrease, because if the denominator decreases, the left hand side will get increase. Okay, so we'll see what is the output resistance. So as I have already told, so to find the output resistance, so what we have to, we need to make the input source 0, whether it is a voltage or current. We need to make source 0, break up the circuit to apply a test voltage Vt. So whatever the load is connected, we need to detach that, remove it, and we need to apply some voltage Vt. Okay, so applying KVL to this part, applying KVL to output side, so minus Vt plus I naught R naught plus Ai is equal to 0. So Vt is equal to I R naught plus Aii. So for Ii, we know Ii is equal to Is minus If, but Is is equal to 0, therefore Ii is equal to minus If. So what is If? If is beta V0. So Ia is equal to minus beta V0. So what I have done, so Vt is equal to V0. So V0 were applying. So I have written, so Vt is equal to I R naught minus A beta V0. So I have taken this to the left hand side. So V0 is equal to A beta V0, because Vt is equal to V0, I R naught remains on the right hand side. If I take V0 common, 1 plus A beta will be left over. So I have interchanged. I have taken I to the denominator on the left hand side, and I have taken 1 plus A beta to the right hand side. That is, what is V0 divided by I is V0 divided by I. So Vt or Vt divided by I, both are same. Have ROF, that is the output resistance ROF. So ROF is equal to R0 divided by 1 plus A beta. So that is the output resistance decreases by connecting the shunt feedback at the output. That is, the output resistance is decreased 1 plus A beta times of R0. Okay, so since this is in the denominator, if the feedback beta increases, ROF decreases. Okay, so this is all about transresistance amplifier. Thank you.